So in the last video we've talked about a few things, and well, the last subject of interest was actually dependent equations, and we've already introduced a few things. We've talked about a few things. So as you can see here, I'm just waiting for the page to load, so just give it a sec. So in systems of well, matrices, we've already seen how to solve for echelon form and reduced echelon form, and then we've seen how the graphs actually change. So every time you get rid of so going row echelon form, you're basically setting that plane of the equation parallel to the axis where that variable is actually 0. So in this case, it's parallel. This equation is parallel to the x-axis, and it's parallel, and this one is parallel to the x and y-axis. And if you go for reduced echelon form, you're basically forming a perpendicular lines like this. In this case, you see everyone is parallel to the other. So one is parallel to x and to y and z. So in this case, it has to be this one. And for the other one, it's this one. And for the z-axis, it's actually, sorry, this is the z-axis, and this is the this is the deal. Yeah, and you can see here that basically we've done that, we've seen that, and we've solved for that. And in the reduced echelon form, you can just obtain these three results. They will equal to the variables that we're looking for. Right. So to reach the reduced row echelon form, you just usually go for Gauss-Jordan elimination. No. In which you just try to get zeros on top of where the what do you call it? The what's the term again? For what's happening to my vocab? Yeah, the diagonal. What the hell? Whatever. Yeah, that's that. Then we've also talked in the last video about dependent equations, and we've seen that independent equations, so independent systems usually have, and where we talked when we were talking about slopes, dependent systems meant that when you have two equations, dependent systems, one goes dependent on the other, so they have the same set of results, and this is infinitely many results. But the things change when you have more than two equations. As you see, this is a dependent equation. This is a system consists of system dependent equations. You have infinite many solutions, but this is in the case of two equations. When things start to change, as you can see. This is dependent systems, and you usually decide if the systems are dependent in infinitely many solutions is one equation is a multiple of the other, like this. There's a multiple of other, like you can go both ways. This is a dependent system. However, again, things change if you have more than three equations. Now, regardless of the number of variables, dependent equations, more than two equations, then there are considerations which are down below. And these are the other. Now, if you have planes, basically, you're still talking about the number of equations. You remember? Anyways, so going down to where we start talking about more than two equations. Yes, it's right about here. We start to have what you call if the equations are multiples of each other, then those are dependent. However, when you have more than two equations, we opt for linear combination. See the linear combination, meaning so they have a system. Two of these functions form a third function. Now that's a linear combination, so this would be dependent on the other two. The resulting equation made from adding two equations multiplying each one by a constant. So regardless, I mean, you just multiply by a constant linear combination. It doesn't really matter how you really obtained it. But yep, I'm not sure what's going on. Yeah, it's still loading. But you get the notion of this. It's like you get the third equation here, and a linear combination of other equations in the group. That's very important to have the word group in there. And then in this case you'll have other considerations as well. So it doesn't really have to be that it doesn't really have to mean or have to be that the two equations overlap each other. So it can have other considerations as well, as in it can have other considerations as well. So that the solution can have only there could be many solutions, and there could be no solution, and there could be a single solution. Now in the case where you have like these, you see these are multiples, these are dependent systems, but there is only one solution in them. And there is another example here. Now these are two equations, so it really doesn't matter. And this is another two equations where there is no basically multiples of each other. Dependent, because we have two functions that are linear combinations of the other. So in the case where you have three functions here, it's not showing here for some reason. The internet is quite lousy today. But anyways, so you have one function that's a multiple of the other, that's multiple systems. And this is not really, I really can't see it, so I really can't tell if it's a multiple of the other or not. But so it's parallel to this one. It's a third equation. It's parallel to this one, to these two. So the system is still dependent, but because you have two equations that are, so as long as there are two or more dependent functions, then it's a dependent function regardless of contains no dependent equations. So regardless of the number, it contains dependent equations. So as long as there is one or more dependent equations, then the system is a dependent system. The rest is up to how the other functions, more than two, actually react to each other. So that was very important for us to remember and to keep in mind, because it saves us a lot of trouble down the line. Anyway, so again, just to really have a super quick recap. Now if you have two functions, obviously and logically, if those two functions are dependent on each other, then you have a dependent system, and that could only mean one thing. You have infinitely many solutions. Now if you have more than two equations, then things start to change a bit. Now you could have one equation that's dependent on other two, and you could have so you could have like three dependent equations, three of them, again more than two. So the third one would be dependent on some other equations in the group. In that case, you have a single dependency, and it would mean that the system is dependent. So the definition is, as long as there is one or more dependent equation within the system, then that's it. It would mean the system is dependent. However, it does not have to necessarily always mean that the dependent systems are always overlapping each other. So what you could have here is that you could have these systems together, but they don't overlap. They have a single solution, like in this example here. Or better yet, they could have no solution whatsoever. Like you have these two equations depending on other, which have infinitely many solutions, but the third equation is actually parallel to them. Changes you made may not be saved. Come on. Yeah, whatever. You just made a single simple change. Okay. It's loading like super slowly. Yeah. Let me pause the video for a second just to see what's going on with the connection. Oh, it's loading back. So hopefully it loses everything. Yep, it works. Probably just hang there or something. So Magic's called. It's like. So in this case, you have like a dependent system where you have one equation that's dependent on the other. Like if you multiply this by 3, negative 3, you will get negative 1, and this one by something -1, you would probably get the same result, wouldn't you? Well, these two, no, sorry, you could have this dependent on this. It's a multiple, so these are dependent. This may not be dependent, but still have a single solution here. And the same here. So this one is not actually dependent on these two. So you have no solution whatsoever. And the same applies for planes. Now you have these three equations that are dependent on each other. And you still have a single solution. There is no solution in this, yet they are dependent equations. So that's what you keep in mind. So dependent systems contains equations, single one or more dependent equations, and contains no dependent equations. So there's no single dependent equation. That's about it. Okay, so let's see what we've got. So we talked about slopes. We were talking about the matrices. We've done a good chunk. We didn't do exercises on those, so we should consider doing some exercises on that. Let's see where we are at. So in this set of series, Gauss-Jordan animation dependent systems. I think we should be doing this next. Let's see.
And welcome to YU. In the previous lecture, we saw that a system of linear equations is called a dependent system if it contains any equations which are dependent.
Yep, so any equations that are dependent. Now, one thing to I'm not sure where we download here. I think we could link this to a page. Instead of waiting for us to link it. Okay, so let's see the slope. Let's go to the slope. So one thing to consider here is that so I've done so this is basically another video that we will be adding later, but generally speaking, when we talked about dependent and independent systems, one thing that was pretty obvious to us was that well, when you have dependent systems, sometimes you have three equations that are fully dependent on each other, as in they are multiples of each other, like three equations that are multiples of each other. Usually this is just a single plane. And then you could have three different equations that are linear combinations of each other. And this would mean that each equation would represent its own plane. And for that matter, each would have its own set of solutions, or each would have its own set of solutions. So as I was saying, we're just invited to lunch. So as I was saying, once you have the three dependents, so each equation would have its own set of plane, but they were all would share the same solution set. And in that sense, you would see them like in this. They had each plane has its own orientation, but they would have the same solution set. When you go for the reduced echelon form, you would simplify the set of equations, and you would get a whole different set of planes, but with the same solution set. And then you would go for the parametric equations, which we have seen in another video here. So with the parametric equations, you would turn the so when you have an equation with different variables, you can represent those variables in what's called a parametric form. which is you set the variable to equal one of the variables will equal to t, and then you would replace that on replace the other equations. Yeah, this is the parametric equation. So each of the equations, let me check again. Yeah, so you have a single equation where you have an x, y, and z, three different variables. You decide to choose one. You set, for example, x to equal t, and rho to equal t plus 1, and this to equal 3t minus 3 or so. Forgot what that was. Parametric equations. And then, as you can see, when you set z to equal to t, and order triple 3x minus 3. Okay, so y plus z, y plus t equals 1. And we have t plus 1. 1 would equal, yeah, so in this case you'd have y plus t equals 1. So y would equal y minus t. And then you just replace y minus t in every presence of y. You would get the x. Yeah, okay. Can't remember. So parametric equations, we have to take a look. They're not accepted. I want you to check my quality. I think it was one of the videos where we introduced parametric equations. I'm not sure which function, which video was it. Parametrically, yeah, parametric equations.
On Schmohawk and Welshon in a system of three linear equations in three variables. We can describe the solution either by using three equations or represent it as an ordered triple, which gives us the values of the x, y, and z coordinates of the solution point. We have also seen that if during the process of solving a consistent system of equations, we obtain an equality between two equal numbers, then this indicates that the system has infinitely many solutions. These solutions are any solution when all the equations are solutions. Fortunately, it is easy to spot this condition, since when the equations are written in standard form, ax plus by plus cz equals d, any equations which are multiples of each other will describe the sum can all. We need some other way to describe a solution set whose graph is a line in three-dimensional space. Since a line in three dimensions is a linear object,
I think I've described it here. Should have adding to 3.
You might think that it could be described by a linear equation in x, y, and z. But as we have seen, linear equations in three variables describe planes, not lines. In order to mathematically describe a line in three-dimensional space, we need a way to define the values of the three coordinates at every point along the line. This can be done by creating a group of parametric equations, one equation for each of the three coordinates. Each parametric equation expresses the value of one coordinate as a function of an additional variable called a parameter. In this example, we have chosen the letter t to represent this parameter. Equations determines a corresponding value for one of the three coordinates. For example, the values of x, y, and z could be equal to t, t plus 1, and 3t minus 3. So each value of t corresponds to an ordered triple, which describes the position. The parameter in this example, the line represented t, representing it, whose the letter t to a line in three-dimensional space, can be described using three parametric equations.
So parametric equations is just a way for us to describe an equation with three different variables. So if an equation of three different variables represents a space in a 3D plane, then you can't simply describe it to the linear equation. That's why you need a parametric. Anyways, next we'll explore dependent equations with more depth and Jordan-Gauss elimination. You might have to revisit parametric equations, I guess. Quickly read what I've written. See, solution set is described by the equation only in this case where the planes overlap. Only in this case when a line is shared, it's described differently because remember the three variables in an equation indicate a plane. A line is not a plane. So what one could do is describe the points on